fields. While Davis and Bacall struggled with solar neutrinos, other scientists at the time were having great success with atmospheric neutrinos. These neutrinos are formed when cosmic rays collide with upper atmosphere at high velocities. Such collisions create a shower of particles, one of which being a pion. Pions are the manifestation of the strong nuclear force when it has been released from an atomic nucleus. The pion decays in only about 1/100th of a microsecond into a muon and a neutrino. A muon is similar to an electron, except that it has more mass and is less stable. When muons decay into electrons, they release a neutrino and an antineutrino. All of these atmospheric neutrinos carry relatively high energies when compared to their solar cousins. Mel Schwarry noticed this and wrote a paper in 1960 explaining how high-energy neutrinos would be more prone to interaction with matter than lower-energy neutrinos. Here is where Pontecorvo re-enters the scene with another of his brilliant insights. He explained that if muons were literally heavy electrons, then when they decay they should simply radiate off energy as a photon to return to its normal state. However, this had never occurred. Two neutrinos were always emitted off instead. To account for this, he suggested that the muon had a different flavor than an electron, and so the neutrinos that they emit also have a different flavor. Therefore, all neutrinos are not the same. They carry a sort of identity card of where they came from. Mel Schwartz and his team tested this theory at the Brookhaven reactor by firing protons at beryllium targets to produce pions which decay into muons. A 13-meter-thick barrier of steel would stop these muons while their neutrinos pass straight through. The neutrinos would then encounter 10 tons of aluminum, where some neutrinos would pick up an electric charge and produce either a muon or an electron, depending on their flavor. After 10 days, 100 million neutrinos were produced, and only 51 interacted with the aluminum, all of which produced muons. This experiment confirmed that there were at least two flavors of neutrinos, electron and muon. In 1976, a new particle called a tauon was discovered to be like a large muon and therefore has its own neutrino. Atmospheric neutrinos seem to be nice in theory, but large-scale experiments would be required to confirm anything. Davis was the first and only scientist looking for neutrinos at the time, but his apparatus was not quite sensitive enough to detect atmospheric neutrinos. A strange twist of events leads to another team of scientists to detect these neutrinos. Kamiokande was an experiment in Japan that was looking for a theoretical phenomenon called proton decay. To do this, they built a huge tank deep under a mountain in the Kamiokawa mine, which could hold ultra-pure water. This tank was lined with photomultiplier tubes, or PMTs. PMTs work like a light bulb in reverse. They capture light and convert it into an electrical signal. Fortunately for the sake of neutrinos, their experiment failed and proton decay remains no more than a theory. But what did they do with a huge underground tank? The only thing it was useful for now was neutrino detection, an unpopular mission they took as a last resort. Kamiokande was able to do this because of a phenomenon known as Cherenkov's light. The speed of light slows down when it passes through a medium, such as air or water. While nothing can travel faster than light in a vacuum, this is not true in such a medium. When a light particle, such as an electron or muon, travels faster than light in the ultra-pure water, a sort of luminescent sonic boom occurs called Cherenkov's light. An atmospheric neutrino could pick up a charge from the water, turn into an electron or a muon, depending on its flavor, traveling faster than light. The PMTs would sense this light and record it. Not only could Kamiokande record the event, it could record the energy, direction, and flavor of the neutrino. The direction was found by determining where on the PMT sensor the light was absorbed. The energy was found by the intensity of the light. The flavor was determined with a little insight on quantum mechanics. Muons have no electric charge, so when they passed easily through the water and produced a crisp circle of light on the PMTs. However, because electrons have a negative electric charge, they were deflected in various directions as they traveled through water. When the light would contact the PMTs, it would be sensed as a circle of light with fuzzy edges. In 1996, Kamiokande was reconstructed with 10 times the amount of water. This came to be known as Super Kamiokande, or Super K. Super K's science was clean and the methodology logical, so when some unexpected results were found, many eyebrows were raised. When pions decay, a muon-flavored neutrino was predicted to be emitted alongside the muon. In turn, when the muon decays, a muon-flavored antineutrino and an electron-flavored neutrino were believed to be produced with the electron. This yields a 2-to-1 ratio of muon to electron-flavored neutrinos. Super K did find that more neutrinos were of the muon flavor, but not as much as were expected. In addition, this deficit of muon neutrinos was even larger when they came from close to the horizon than when they came from straight above. Something was happening to the neutrinos mid-flight that was previously unpredicted. Again, Bruno Pontecorvo's ideas would provide the solution for others to investigate. Quantum theory allows for some bizarre phenomenon. Pontecorvo realized that if different flavors of neutrinos have different masses, which we now know they do, then they would have different quantum frequencies. Quantum theory allows for a single neutrino to be a hybrid of two different flavors, and so simultaneously have two different masses. This implies that there are two slightly different frequencies disguised as one particle. The difference in frequencies produces a sort of beat frequency of identity. When the frequency aligns itself in the original orientation, it will appear to be fully electron or muon flavored. Even stranger is that we can only observe one flavor, whichever the beat is closest to. Now that we know three types of neutrinos exist, we know that there are actually three frequencies interfering in unison. Pontecorvo describes this as neutrino oscillation. This can be linked to Escher's drawing of metamorphosis. A pattern that appears to be a bird at the top of the page progressively morphs into a fish as it approaches the bottom. The picture near the middle can only be described as a bird-fish hybrid. By 1999, a new experiment was built to measure solar neutrinos. The experiment was called the Sudbury Neutrino in Ontario, or SNOW. SNOW was capable of doing more than all of its predecessors. It could detect all three types of neutrinos. This was made possible by the use of something called heavy water. Heavy water is similar to the standard H2O, except that the hydrogen atoms have been replaced with deuterium, a proton and a neutron. Detection was then possible because when an electron neutrino hits an atom of deuterium, it splits the atom and steals a negative charge from the neutron. The result will be an electron and two protons. The muon and tau neutrinos do not have this ability, but they can bounce off the deuterium, splitting the atom but otherwise leaving it unchanged. When SNOW's results were paired with SuperK's, they found that Bacall's calculations had predicted the correct number of electron neutrinos that the sun emitted, and Davis's experiment had sensed the correct number of electron neutrinos that remained after they oscillated their way to Earth. Upon receiving confirmation of his calculations, Bacall exclaimed, "I feel like dancing. I'm so happy." It is an important side note that on September 2001, the Oscillation Project with Emulsion Racking Apparatus, or OPERA, in the CERN laboratory in Europe, detected neutrinos that were traveling faster than the speed of light in a vacuum. More research must be done before anything is definite, but theorists predict that this may be evidence of higher dimensions that the neutrinos use as a shortcut. If the results are accurate, this will be the most important scientific discovery of the century.